Every human being alive today is protected by an invisible life support system so reliable that most people never think about it. At this moment, air presses gently against your skin from every direction. Oxygen moves into your bloodstream with each breath. Earth's magnetic field silently redirects high-energy particles away from the surface. Above the atmosphere, dangerous radiation travels constantly through space, but almost none of it reaches you. Life on Earth exists inside an extraordinarily narrow range of conditions. Not because the universe is naturally friendly to biology, but because this planet continuously shields living organisms from environments that would otherwise destroy them. Human beings evolved entirely within these conditions. Every organ inside the body assumes the presence of gravity, atmospheric pressure, stable temperatures, and breathable air. Remove any one of those systems, and the body begins struggling almost immediately. Consider oxygen first. Earth's atmosphere contains roughly 21% oxygen. That number may sound arbitrary, but small changes create serious consequences. Too little oxygen starves tissues and organs. Too much oxygen increases fire risk and damages cells over time. Human respiration evolved around a remarkably precise balance, but oxygen alone is not enough. The atmosphere must also maintain pressure. At sea level, atmospheric pressure measures approximately 14.7 pounds per square inch. That pressure pushes equally across the body at all times. Inside the bloodstream and lungs, gases remain dissolved because external pressure keeps them stable. A useful way to think about this is to imagine a deep-sea fish suddenly pulled to the ocean's surface. The environment changes faster than the organism can adapt. In many ways, humans exposed to space experience the opposite problem. Instead of moving from high pressure to lower pressure underwater, the body is suddenly exposed to almost no pressure at all. Even simple biological actions depend on this equilibrium. Breathing works because pressure differences move air into the lungs. Blood circulation depends on stable fluid dynamics. Cells exchange gases continuously under conditions the planet maintains automatically. There is also the matter of radiation. Earth's atmosphere absorbs large amounts of harmful ultraviolet radiation before it reaches the surface. Above that atmosphere, the planet's magnetic field acts like a gigantic protective barrier. Charged particles from the Sun are redirected around Earth instead of striking the surface directly. Teaching insight. Astronauts aboard orbiting spacecraft often describe Earth's atmosphere as surprisingly thin when viewed from space. From orbit, the layer protecting every forest, ocean, city, and human being appears almost fragile. And in a scientific sense, it is. Without Earth's layered protections, humans would not slowly become uncomfortable. Survival would begin collapsing within seconds. Deep space removes nearly every condition the human body depends upon simultaneously. No breathable air, no atmospheric pressure, no magnetic shielding, no stable temperatures, no natural defense against radiation. The universe beyond Earth is not designed for human biology, which leads to the first and most immediate danger awaiting any unprotected person in space: the complete loss of pressure itself. The moment atmospheric pressure disappears, the human body enters an environment it has never evolved to handle. Popular films often portray this as an instant freezing process, but physics tells a very different story. In reality, vacuum exposure begins by disrupting the pressure equilibrium that keeps every fluid and gas inside the body stable. Under normal conditions, gases dissolved in the bloodstream remain compressed by surrounding atmospheric pressure. The same principle allows carbon dioxide to stay dissolved inside a sealed soft drink bottle. Once the bottle is opened, pressure drops and gas rapidly escapes in the form of bubbles. A similar process occurs inside the body during vacuum exposure. As external pressure approaches zero, dissolved nitrogen, oxygen, and carbon dioxide begin coming out of solution. Gas bubbles form throughout tissues and blood vessels in a condition known as ebullition. Circulation becomes increasingly unstable as these bubbles interfere with normal blood flow. At the same time, another process begins affecting water itself. Many people associate boiling with heat, but boiling is actually controlled by pressure. Lower the surrounding pressure sufficiently, and water can boil at surprisingly low temperatures. In near vacuum conditions, water exposed to the environment can begin vaporizing at ordinary body temperature. This does not mean the body instantly turns to steam. Human skin provides some containment. Internal blood pressure also prevents complete vaporization. But moisture exposed directly to vacuum behaves differently. Saliva on the tongue begins boiling. Tears and moisture on the eyes start vaporizing. Fluids lining the lungs become unstable almost immediately. Teaching insight. Mountaineers climbing extremely high altitudes experience a mild version of pressure reduction. At elevations above about 8,000 meters, oxygen levels and air pressure fall low enough to impair judgment and threaten survival. Space represents that problem taken to its absolute limit. The lungs face perhaps the most immediate mechanical danger. Inside the chest, gases naturally expand as surrounding pressure drops. If a person instinctively holds their breath during exposure to vacuum, expanding air can rupture delicate lung tissue within seconds. This is why astronauts are trained never to hold their breath during depressurization emergencies. Meanwhile, oxygen delivery to the brain begins collapsing. The brain represents only a small percentage of total body mass, yet it consumes roughly 20% of the body's oxygen supply. Neurons function continuously and have very limited oxygen reserves. Without fresh oxygen entering the bloodstream, cognitive function deteriorates rapidly. Within approximately 10 to 15 seconds, consciousness fades. Importantly, this process is not driven by pain or dramatic external injury. It is driven by gas laws, fluid dynamics, and thermodynamics. The human body depends completely on stable pressure conditions maintained by Earth. And even if exposure lasts only briefly, vacuum is not the only invisible threat waiting beyond the atmosphere. Deep space is also filled with high-energy radiation, moving silently through the solar system and far beyond it. Beyond the immediate dangers of vacuum, space contains another threat that cannot be seen, heard, or felt directly. It moves continuously through the universe at enormous speeds, passing through spacecraft walls, electronic systems, and living tissue alike. Radiation in deep space is not a secondary problem. For long-duration missions, it becomes one of the central limits of human survival. On Earth, life exists beneath multiple protective layers. The atmosphere absorbs large amounts of incoming radiation before it reaches the surface. Above that atmosphere, Earth's magnetic field redirects many charged particles away from the planet entirely. Without these defenses, conditions change dramatically. The Sun constantly releases radiation across the solar system. Some of it arrives as ultraviolet light. Some comes as streams of charged particles carried by the solar wind. During solar storms, the intensity can increase rapidly, exposing astronauts to dangerous radiation doses within hours. But the most serious long-term threat comes from galactic cosmic rays. These particles originate far beyond the solar system. Many are atomic nuclei accelerated to extraordinary speeds by violent cosmic events such as supernova explosions and neutron star collisions. Some travel through interstellar space for millions of years before eventually crossing paths with a spacecraft. When these particles strike the human body, they do not behave like ordinary sunlight. They penetrate deeply into tissue, ionizing atoms and damaging molecular structures along their path. DNA becomes one of the primary targets. Cells possess repair mechanisms capable of correcting some radiation damage, but high-energy particles can create complex breaks that cells fail to repair correctly. Over time, mutations accumulate, cancer risk rises. Damage to blood-forming tissues, the nervous system, and internal organs becomes increasingly likely. Teaching insight. Radiation exposure is measured not only by quantity, but by biological impact. Different forms of radiation deposit energy into tissue differently. A small amount of high-energy cosmic radiation can be far more damaging than a larger dose of lower-energy radiation on Earth. Astronauts aboard the International Space Station already experience this reality. Even within low Earth orbit, where partial magnetic shielding still exists, astronauts receive radiation doses estimated at roughly 150 to 200 times higher than average levels on Earth. Future missions traveling beyond Earth's magnetic field would face significantly greater exposure. NASA studies suggest that a round-trip mission to Mars could increase an astronaut's lifetime cancer risk by approximately 5%. That estimate does not fully account for every possible neurological or long-term biological effect still being studied. Shielding remains a major engineering challenge. Dense materials can block some radiation, but effective protection against galactic cosmic rays would require extremely heavy shielding. Every kilogram added to a spacecraft increases launch complexity, fuel demands, and mission cost. In other words, humanity currently possesses the technology to reach deep space, but not yet the ability to make it entirely safe. And while radiation damages the body slowly over months and years, exposure to vacuum follows a far more immediate timeline measured in seconds. Radiation may threaten astronauts over months or years, but vacuum exposure operates on a far shorter timescale. In the absence of protection, the human body begins failing within seconds. Scientists understand this process with surprising precision because the underlying mechanisms are governed by predictable physical laws. Pressure loss, oxygen deprivation, gas expansion, and circulatory failure all follow a measurable sequence. The timeline begins the instant atmospheric pressure disappears. At 0 seconds, the body suddenly loses the external force that normally stabilizes internal gases and fluids. Air remaining inside the lungs immediately starts expanding. Within the first second, moisture exposed to vacuum begins vaporizing. Saliva on the tongue starts boiling. Tears and thin moisture layers on the eyes become unstable. By roughly 2 seconds, gas bubbles form more aggressively throughout tissues and blood vessels. Blood itself does not instantly boil because the circulatory system maintains internal pressure, but dissolved gases begin disrupting normal circulation. Around 6 seconds into exposure, cardiovascular function becomes increasingly compromised. Blood flow grows less efficient as bubbles interfere with circulation and oxygen transport. At approximately 10 seconds, oxygen levels inside the brain fall below the threshold required for normal awareness. Then consciousness disappears. Most estimates place loss of consciousness near 12 seconds after exposure begins. Importantly, this occurs before many of the more visibly severe effects fully develop. Teaching insight. The brain is exceptionally sensitive to oxygen deprivation because neurons cannot store meaningful oxygen reserves. Unlike muscles, which can continue briefly under low oxygen conditions, brain tissue begins failing almost immediately when oxygen delivery stops. Meanwhile, the body itself continues changing. Swelling becomes increasingly noticeable as gases expand throughout soft tissues. Skin elasticity prevents the body from bursting, contrary to many fictional depictions, but expansion can still become severe. The heart may continue beating temporarily after unconsciousness occurs. However, circulation is steadily collapsing. Without rapid repressurization and oxygen restoration, irreversible injury becomes unavoidable. At around 60 seconds, prolonged oxygen deprivation begins causing serious brain damage. The exact timeline can vary slightly depending on conditions and individual physiology, but survival probability decreases rapidly after this point. Near the 2-minute mark, cardiac activity and brain function cease entirely. This sequence is not theoretical. During a 1965 NASA vacuum chamber accident, technician Jim LeBlanc was accidentally exposed to near vacuum after a suit hose disconnected. Before losing consciousness, he later reported feeling saliva boiling on his tongue. Emergency repressurization restored pressure after roughly 14 seconds, allowing him to survive with no permanent injury. The incident demonstrated two important realities simultaneously. First, the human body cannot survive prolonged vacuum exposure unprotected. Second, extremely rapid rescue can sometimes prevent permanent damage if exposure time remains brief. But relying on rescue alone is impossible during routine operations in space. To work safely outside a spacecraft, astronauts require portable systems capable of replacing nearly every environmental condition Earth normally provides automatically. That requirement led engineers to create one of the most sophisticated survival machines ever worn by a human being. To prevent the chain of failures caused by vacuum exposure, Astronauts carry an artificial environment around their bodies every time they leave a spacecraft. A modern spacesuit is not simply protective clothing, it is a compact life support system designed to replace the critical functions Earth normally provides for free. In practical terms, a spacesuit functions like a personal spacecraft. It must maintain internal pressure, deliver breathable oxygen, remove carbon dioxide, regulate temperature, provide communication systems, and shield the astronaut from radiation and micrometeoroids. All of this must operate continuously while allowing a human being to move, work, and think clearly in one of the harshest environments ever encountered. Pressure management is one of the first engineering challenges. Earth's atmospheric pressure at sea level measures approximately 14.7 pounds per square inch. Fully reproducing that pressure inside a flexible suit would make movement extremely difficult. Engineers therefore reduce suit pressure while increasing oxygen concentration. NASA's modern extravehicular suits typically operate at around 4.3 pounds per square inch using nearly pure oxygen. This lower pressure prevents embolism, while still allowing astronauts to bend their arms, operate tools, and move through space with manageable resistance. Even so, mobility remains physically demanding. A pressurized suit naturally resists bending, because the internal gas pushes outward continuously. Astronauts often describe routine hand movements during spacewalks as similar to squeezing a stiff rubber ball repeatedly for hours. Teaching insight. Before leaving a spacecraft, astronauts spend time breathing pure oxygen to remove dissolved nitrogen from their bloodstream. This process reduces the risk of decompression sickness, a condition divers know as the bends. Breathing support presents another critical requirement. The suit continuously supplies oxygen while removing carbon dioxide exhaled by the astronaut. Without active filtration, carbon dioxide would rapidly accumulate inside the helmet and become toxic. Many systems use lithium hydroxide canisters that chemically absorb carbon dioxide from circulating air. Fans maintain airflow throughout the suit because natural convection behaves poorly in microgravity. Temperature control introduces an entirely separate problem. On Earth, the body cools itself partly through convection, as surrounding air carries heat away from the skin. In vacuum, convection does not occur. Heat transfer becomes far less efficient. Without cooling systems, astronauts working inside pressurized suits could overheat surprisingly quickly. To solve this problem, astronauts wear liquid cooling garments beneath the outer suit layers. Thin tubes circulate water around the body, transporting excess heat away from the skin and into external radiators. The outer layers of the suit serve additional functions. They protect against abrasive dust, small debris impacts, and intense temperature swings between direct sunlight and shadow. In orbit, surfaces exposed to sunlight can become extremely hot, while shaded regions can plunge to dangerously low temperatures. Fully assembled, a modern NASA spacesuit weighs roughly 280 pounds on Earth and costs millions of dollars to design, maintain, and operate. And despite decades of engineering refinement, these systems remain vulnerable. Because in space, even a relatively small equipment failure can escalate into a life-threatening emergency with extraordinary speed. Even the most advanced survival systems used in space operate with very little margin for error. A modern spacesuit can sustain human life in vacuum, but only while every critical subsystem continues functioning correctly. In deep space, small failures do not remain small for long. One of the most dangerous examples involves oxygen itself. Spacesuits commonly use high-concentration oxygen environments because they simplify pressure management and reduce suit complexity. But oxygen creates an important engineering trade-off. Materials that burn slowly in normal air can ignite far more aggressively in oxygen-rich conditions. This danger became tragically clear during the Apollo 1 disaster in 1967. Astronauts Virgil Grissom, Edward White, and Roger Chaffee were conducting a launch rehearsal inside a spacecraft cabin filled with high-pressure pure oxygen. During the test, an electrical spark ignited flammable material inside the capsule. The fire spread with extraordinary speed. Within seconds, cabin temperatures and smoke levels became fatal. The crew could not open the inward opening hatch quickly enough to escape. Teaching insight. Engineers often describe spacecraft design as a process of managing competing risks rather than eliminating them entirely. Systems optimized for one problem frequently create new vulnerabilities somewhere else. The Apollo 1 fire permanently changed spacecraft engineering standards. NASA redesigned cabin materials, altered atmospheric procedures, and improved hatch systems to reduce future fire risk. But fire is not the only danger spacesuits face. In 2013, European Space Agency astronaut Luca Parmitano experienced a near-fatal malfunction during a spacewalk outside the International Space Station. Water from the suit's cooling system began leaking into his helmet. Under normal gravity, leaking water would fall downward. In microgravity, the water behaved differently. It spread across his face and floated around his head, gradually covering his eyes, nose, and mouth. Parmitano could no longer see clearly. Communication became difficult. Breathing also became increasingly dangerous as water accumulated inside the helmet. Despite the severity of the situation, the initial warning signs seemed relatively minor. That is one of the defining characteristics of emergencies in space. Small technical abnormalities can escalate rapidly because the surrounding environment offers no natural protection. Parmitano successfully returned to the airlock, but engineers later discovered that more than a litre of water had collected inside the helmet. The incident demonstrated how survival in space depends not only on engineering sophistication, but on constant monitoring, disciplined procedures, and immediate response capability. Spacesuits also face strict operational limits. Oxygen supplies remain finite. Carbon dioxide filtration systems eventually saturate. Battery capacity declines over time. Cooling systems must continue circulating heat without interruption. For this reason, most spacewalks are carefully timed to remain within safe consumable limits, often lasting 6 to 8 hours. Every minute outside a spacecraft represents a balance between human capability and environmental hostility. And beyond the suit itself lies another uncomfortable reality. The spacecraft protecting astronauts are also fragile structures, separated from vacuum by barriers far thinner than most people imagine. Even after solving the immense challenge of keeping a human alive inside a spacesuit, astronauts still depend on something equally fragile around them, the spacecraft itself. Most people imagine spacecraft as thick, armoured machines built to withstand extreme punishment. In reality, many sections are surprisingly thin. The reason is simple physics. Launching mass into orbit is extraordinarily expensive. Every additional kilogram requires more fuel, larger rockets, and stronger structures to support the added weight. Engineers therefore reduce mass wherever possible. As a result, the walls separating astronauts from vacuum are often only a few millimeters thick. Certain modules aboard the International Space Station use pressure walls comparable in thickness to only a few stacked coins. Despite that thinness, those walls must continuously maintain cabin pressure while surviving vibration, radiation exposure, and debris impacts. Teaching insight. Spacecraft engineering is often a process of compromise. Stronger walls improve protection, but heavier spacecraft become dramatically harder and more expensive to launch. Orbit itself is also far from empty. Earth is surrounded by debris left behind by decades of launches, satellite failures, and collisions. Some objects are large enough to track from the ground. Many smaller fragments are not. The danger comes from velocity. Objects in low Earth orbit commonly travel faster than 28,000 kilometers per hour. At those speeds, even tiny particles carry enormous kinetic energy. A paint flake striking a spacecraft can hit with force comparable to a bullet. Small metal fragments and micrometeorites can puncture exposed surfaces or damage critical systems. To reduce this risk, spacecraft use layered protective systems called Whipple shields. Instead of relying on one thick wall, engineers place multiple layers separated by small gaps. When debris strikes the outer layer, the object fragments and spreads its energy before reaching the inner hull. But no shielding system is perfect. Large debris impacts remain one of the most serious threats in orbit. The International Space Station occasionally performs avoidance maneuvers to reduce collision risk from tracked objects. One of the most feared emergencies during any mission is depressurization. If cabin pressure begins dropping rapidly, astronauts may have only seconds to isolate damaged sections or activate emergency systems. This danger became tragically real during the Soyuz 11 mission in 1971. As the Soviet spacecraft prepared for re-entry, a valve opened prematurely during descent, causing sudden cabin depressurization. Cosmonauts Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov were not wearing pressure suits. By the time the capsule landed, all 3 crew members had died from asphyxiation. The accident permanently changed spacecraft safety procedures. Future crews began wearing pressure suits during critical phases of flight to improve survival chances during sudden pressure loss. Even today, astronauts survive inside lightweight structures, moving through vacuum at extraordinary speed, protected by barriers far thinner than most people imagine. And keeping humans alive inside those fragile machines requires another complex system operating continuously in the background: life support itself. Keeping astronauts alive inside a spacecraft involves far more than supplying oxygen and sealing the cabin from vacuum. Long-duration missions require the creation of a small artificial ecosystem capable of functioning continuously for months or even years. In low Earth orbit, regular resupply missions from Earth remain possible, but the farther humans travel into deep space, the more independent these systems must become. This is why recycling becomes essential. Modern spacecraft are designed to recover and reuse as many resources as possible. A useful example is the International Space Station, where approximately 90% of onboard water is recycled. That includes moisture collected from sweat, condensation, and even urine. On Earth, people rarely think about water because it is constantly available. In space, every kilogram launched into orbit carries enormous cost. Recycling, therefore, becomes a matter of survival rather than convenience. Teaching insight. Astronauts aboard the ISS sometimes joke that today's coffee may contain water molecules recycled from yesterday's breath. Scientifically, that statement is almost certainly true. Oxygen production follows a similarly controlled process. One major system uses electrolysis, a reaction that splits water into hydrogen and oxygen using electrical energy. The oxygen supports breathing, while hydrogen can later be reused in additional chemical processes. Carbon dioxide removal is equally important. As astronauts exhale, carbon dioxide slowly accumulates inside enclosed environments. Without active filtration systems, concentrations would eventually become toxic. Some spacecraft systems use the Sabatier reaction, which combines carbon dioxide with hydrogen to produce water and methane. The reclaimed water can then re-enter the life support cycle. Together, these technologies reduce dependence on Earth-based resupply. But engineering alone does not solve every problem associated with long-duration missions. Human psychology becomes another critical factor. Astronauts live inside confined environments with limited privacy, repetitive routines, and separation from family and natural surroundings. Outside the spacecraft exists an environment instantly fatal to human life. Over time, isolation itself can become psychologically exhausting. Studies conducted in Antarctic stations, underwater habitats, and other isolated environments show that prolonged confinement increases stress, irritability, sleep disruption, and interpersonal conflict. Deep space missions introduce additional complications. Communication delays increase dramatically with distance from Earth. During Mars missions, one-way communication delays can exceed 20 minutes depending on planetary positions. A conversation that feels immediate on Earth becomes slow and fragmented in deep space. This means astronauts must solve many problems independently without real-time support from mission control. The challenge is therefore not only technological, it is deeply human. A crew traveling through deep space must maintain physical health, emotional stability, technical competence, and social cooperation for years inside a closed mechanical environment. And as missions move farther from Earth, those demands become even more severe. Because the greater the distance, the more difficult rescue, resupply, and survival itself become. As missions move farther from Earth, every survival challenge discussed so far becomes more severe. Radiation exposure increases, rescue options disappear, communication slows. Even small technical failures become potentially mission-ending events. A journey to Mars demonstrates this reality clearly. Depending on planetary alignment, the trip from Earth to Mars typically requires 6 to 9 months each way using current propulsion systems. When surface operations and return travel are included, total mission durations may exceed 2 years. For comparison, most missions aboard the International Space Station occur only a few hundred kilometers above Earth, where astronauts still remain partially protected by the planet's magnetic field and can return home relatively quickly if necessary. Mars missions remove those advantages. Astronauts traveling through deep space would remain exposed to cosmic radiation for months without meaningful magnetic shielding. Even with protective spacecraft materials, long-term exposure would steadily increase risks of cancer, nervous system damage, and cellular mutation. At the same time, the human body begins adapting to prolonged weightlessness in ways that create additional medical concerns. Bones continuously remodel themselves in response to mechanical stress. On Earth, gravity constantly forces muscles and bones to support body weight. In microgravity, that stress largely disappears. As a result, astronauts gradually lose bone density and muscle mass. Teaching insight. Some astronauts aboard long-duration missions lose bone density at rates comparable to elderly osteoporosis patients on Earth. Exercise slows the process, but does not eliminate it entirely. The cardiovascular system also changes. In microgravity, fluids redistribute throughout the body, because gravity no longer pulls blood downward toward the legs. Over time, the heart performs less work and can weaken slightly. When astronauts return to gravity environments, many initially experience dizziness, weakness, and difficulty standing. Mars introduces another challenge beyond biology: isolation from immediate help. Low Earth orbit missions still operate relatively close to Earth. Emergency return procedures may require hours or days. A Mars crew would have no such option. If a critical system fails during transit, astronauts must repair it independently, using whatever tools and spare parts exist on board. Resupply missions cannot arrive quickly enough to help. Communication delays make the situation even harder. Depending on planetary positions, radio signals between Earth and Mars can require more than 20 minutes to travel one way. Conversations become delayed exchanges, rather than real-time communication. Future missions deeper into the solar system would magnify these difficulties further. Travel times to Jupiter or Saturn using current technology could extend into many years. Radiation environments around some planets become even more dangerous due to powerful magnetic fields trapping energetic particles. Human exploration beyond Earth remains scientifically possible, but operationally extreme. Every additional kilometer away from Earth reduces flexibility, increases danger, and places greater demands on both technology and human endurance, which ultimately leads to a larger and more philosophical question. If deep space is this hostile to human biology, why does humanity continue trying to explore it at all? After examining vacuum exposure, radiation, isolation, spacecraft fragility, and the biological limits of the human body, an obvious question begins to emerge. Why continue exploring space at all? From a purely practical perspective, robotic missions are often more efficient. Robots do not require oxygen, food, radiation shielding, or psychological support. They can survive environments that would kill humans immediately. Many of the greatest discoveries in modern planetary science were made by robotic spacecraft. Machines have landed on Mars, traveled beyond the solar system, explored Saturn's moons, and photographed distant planets with remarkable precision. Teaching insight, the Voyager probes, launched in 1977, continue sending scientific data from interstellar space decades later. No human mission has ever traveled remotely that far. So, the argument for robotic exploration is scientifically strong, but human spaceflight has never been driven entirely by efficiency. Part of the motivation is exploration itself. Human beings possess a persistent tendency to move beyond familiar boundaries, even when the risks are severe. Throughout history, oceans, deserts, polar regions, and mountain ranges were all once considered environments too dangerous for sustained exploration. Space represents the largest extension of that pattern. There are also long-term survival considerations. Earth will not remain habitable forever. Over astronomical timescales, the Sun gradually becomes brighter as it ages. Scientists estimate that within roughly 1 billion years, rising temperatures may begin destabilizing Earth's oceans and atmosphere. Long before that distant future arrives, nearer-term threats also exist. Large asteroid impacts, supervolcano eruptions, global warfare, engineered pandemics, and ecological collapse all represent potential risks to civilization. None are guaranteed, but history demonstrates that planetary environments can change suddenly and catastrophically. Some researchers therefore argue that becoming a multiplanetary species could reduce the probability of total human extinction. The logic is straightforward. A civilization existing across multiple worlds becomes less vulnerable to a single planetary disaster. At present, however, humanity remains in the earliest stages of that possibility. Every astronaut traveling through space still survives only because of carefully engineered systems separating fragile biology from vacuum, radiation, extreme temperatures, and isolation. Deep space is not naturally compatible with human life. Humans evolved beneath thick atmosphere, stable gravity, liquid water, and magnetic protection. Remove those conditions, and survival depends entirely on technology functioning correctly. In many ways, modern human spaceflight resembles life support more than conquest. Astronauts do not dominate space, they endure it, and yet, despite all the dangers, exploration continues, because scientific curiosity, long-term survival planning, technological progress, and the desire to understand humanity's place in the universe continue pushing civilization outward. For now, the greatest barrier between humanity and the stars is not distance. It is the challenge of surviving the journey itself.